Welcome to week 3, chapter 5, hashing. So, what are we going to cover this week? Well, we're going to look at the fundamentals of hashing, the purpose of hashing, types of hashing algorithms, key concepts, and the key terms and key terminology. Key terms and terminology we're going to be looking at. So, hashing versus encryption. As you know, we've spent the last 2 weeks on encryption, using the different ciphers and how all that works. So encryption is two functions. Let's look at hashing versus encryption. Encryption is two functions. It takes the plain text and converts it over into a ciphertext that no one can read. So it actually changes everything that we're doing. So it makes it difficult to read, it has the security, and it allows us to send information over open airwaves or however we want to, and we don't have to worry about anyone reading it. So encryption, you have to have it goes through the algorithm and it comes out unlegible for the most part. Now hashing produces a fixed length output. It's basically a summary of the file. It takes all the information, looks at it, and converts it to a fixed length output. And this allows us to look at it and do something with it. And we're going to go over what those different things are that we can do. So here's a basic overview of hashing. Basically, it works whether we use plain text or cipher. It doesn't matter what we're saying. If we want to send it in plain text, we can put hashing with plain text, or we can put hashing with ciphertext. Just depends on what we want to do. And it's really a finger, how it's looked at in the industry. It's a digital fingerprint of the data. So if I have a cover letter or a letter that has 1,000 words in it, I'm going to get a certain number. If I add one letter to it, I get a completely different number that comes out of my hashing when we're done. Basically, it doesn't convert data to unreadable text to the ciphertext. It keeps it in it the way it is, and we're going to show you how it's going to be used to ensure that we're getting the same information when we get to the other side. It ensures integrity of the data, and that's really an important part, and I'll get into that in a little bit more. It's not reversible. As we learned with the ciphertext, we could have text, we cipher it, and someone can actually crack that code and look at it and say, all right, this is what that code read. So you're able to crack the ciphertext. With hashing, you just get a digital fixed length output, and you really can't convert it back to what the original text was, because it just doesn't work that way, and as you'll see that in a few minutes. It's basically just one-way encryption. You take that information, you create a fixed length, and that's it. And its main use is used for validating data. And I'm going to go over that again in a little bit more detail for that. Output is a fixed length, and it doesn't have a key. Like with our other encryption processes and ciphers, we always had a key we had to have. Well, there's not a really key with this information. So uses of it: digital signatures, digital certificates. So if you're going to want to sign something digitally, it allows you to say, hey, this is what you sign, and it puts it on. And I think it verifies downloading of software, which is a key thing. So if you have this huge file, what will happen is you're going to put your hashing to it, you get a specific number. Then you download your file. And what happens is after it's downloaded, it runs the hash on it again, hashing on it, and it checks to make sure that the file size has been downloaded correctly. So again, it's a really good way to figure out if you're able to download that information, if it came through correct. If you have, it's verifying emails, it's the same thing. Did all the data come through? Storage of passwords allows us to put information in. Verification of communication, intrusion detection, searches. It's used on all databases. So this is an important part of how everything comes together with hashing. So let's take a look at the hashing algorithms. There's a whole bunch of them that are used. The message digest, which is the first one, it can either be be read as MD2, MD4, MD5, or even MD6. They're the ones that allow it. So the MD2 is a one-way hash function used in the privacy enhanced mail (PEM) protocol along with MD5. The MD4, the message digest 4, is again a one-way hash function used with PGM and other systems. It's not really used much, has been replaced for all intents and purposes by MD5. So MD5 is what we're currently using, and improved and redesigned version of the MD4 producing a 128-bit hash. And that means the length is going to be about 32 characters, will be 32 characters in length. MD5 is still extremely popular, but is being phased out due to some potential weaknesses. And then MD6 is a hashing algorithm designed by Ron Rivest. The HAVAL is a variable length one-way hash function, and it's really just a modification of the MD5. So Whirlpool is a hashing algorithm designed by the creators of AES. Tiger, a hashing that is optimized for 64 bits but works well with them. So it's really made for the 64-bit thing. RIPE-MD is the hashing algorithm commonly used in Europe. So those are just an overview of our hashing. So here's a quick video of how hashing works.
A cryptographic hash is a way to take some existing data. It might be a file, it might be a picture, it might be an email that you've created, and it's a way that you can create a message digest from it, which is really just a short string of text. If you were to look at a cryptographic hash, and we'll look at some in just a bit, you'll see that's just a bunch of letters and numbers put together, usually represented in a hexadecimal form. Now, what's nice about this is if you were to have a file and create a cryptographic hash from it, you could send that file to someone else and you could say, here's the cryptographic hash I created on my side. You do the same thing. And they'll take the file, create a hash from that file. If the hashes match up, then you know the file is exactly the same on both sides. One very important characteristic of these hashes is that it's a one-way trip. I could not look at the hash and somehow figure out what the original text was. That's a very important consideration with hashes, because very often we use these to take passwords and hash the password, and we store the password as the hash. We're not actually storing your actual password in plain text. This makes your storage of the password that much more secure, because if somebody got their hands on this list of passwords or hashed passwords, they would have no idea what your original password was. That's an extremely important aspect of what we do with hashes, but we can also use hashes for other things. For instance, they could be a digital signature. We know that if we were to take a file and create a cryptographic hash from it, we could give that file to someone else, have them also look at that hash and make sure that what they've received is authentic, that nobody changed this file somewhere along the line, and they know that it came from you because you're matching up the keys that you're using to create that hash with. Some very nice capabilities there. That means you don't have to encrypt the entire file that you're sending. You can simply send it along in plain text, but still be assured that nobody changed that file somewhere in between. Let's take an example of this. I'm on the GNU PG webpage. This is the open source version of PGP, an absolutely free version. It's called GNU Privacy Guard. And I have downloaded a file. You can see in this download section that they have a number of files here. And along with the files, they have put the SHA-1 checksum for this. This is the hash of that particular file. And I've downloaded this one right here, this GNU PG 1.4.11 tar-gz, which is supposed to have this checksum. So let's see if it does. I'm going to flip over to my terminal screen, which is right here. Let's move it up so we can see all these things at the same time. Move this down. Here's the file that I've downloaded right here. And let's see if that's really there. Yes, that is. That's the GNU PG 1.4.11.tar-gz that's on my hard drive. And I'm going to check it with that SHA-1 checksum using OpenSSL. and I'm just going to specify as a parameter SHA-1 and then the name of the file. And OpenSSL will perform this SHA-1 checksum for me and create this hash from the file. And ideally, that hash should match exactly what's on the website. And if you compare those two, you can see they are exactly the same. We have mathematically gone through that file, created a hash of it, and now we can be assured that the file that is on my hard drive right here matches the file that was put out there on the web server originally.
So as you can see, hashing allows us to verify certain data. So we were able to take a look at our file that we downloaded, and for most part, this is used quite a lot in the industry, because every time you download a file, you want to make sure you got the exact file, that nothing got corrupted. Because even if it's 1 bit off the file, if 1 bit got thing, that hash would change, because it looks at everything that's in that document and converts it into the hash number, into that fixed number. So it's very useful in making sure that we do get the exact information that we're doing. So some of the things we're looking at is it does authentication, it does the integrity checking, and non-repudiation, as we talked about. So this allows us to take information, send it over the internet or wherever, and ensure that we're going to be able to get that information back, especially when we download it. And so, like in the video, it showed the integrity of it. He had to, he checked the hash from where it started, and when he downloaded, he had that same number. So it allows us to verify what's going on. So as I said, it produces a condensed representation, and it's set to a fixed length. So if I have a 128-bit, whatever it is, that's what it's always going to come out to be. There's no, it's not a depends on anything. Whatever my length is, that's what it is. And it's just a one-way function. I can convert my hash. I take my file, I get a hash out of it. Keeps my file original, as we discussed, but then I get that hash. This way, if I send it anywhere, if there's any changes to it, I can always check that hash to see, making sure that it's there. And you cannot go back, you can't have your hash number and go back and figure out what the message was that it came from. So it doesn't work. As in the video, it showed that this is good for keeping your passwords, because if you put your passwords in a hash, no one can calculate what it is. And it should be derived from the whole message. So what are some uses of it? Well, e-commerce, obviously, every time you buy something, we're going to be using the encryption, and we want to make sure the hash, that nothing got changed. And we want to make sure that the origin is not changed at all. Where did that message come from? We also check the integrity of the message, software distribution, and its trusted timestamp. What are some weaknesses? Exploited weak hash algorithm. If you don't have a good algorithm, you could have some issues. So, not a one-way function. A hash is created from 2 pieces, as described earlier. From what we know, so not a one-way function. The hash is created from the 2 pieces. A fixed length. From what we know so far, the encryption, the more bits that are added to something, the more time it tends to take to break. In fact, the process of break typically takes exponentially amount of power, because of the fact that each hash is so short that it means the average desktop system today would be able to upper cases versus lower cases. In addition to the hashing length, reducing the time it would take to crack using average computer power. The conversion from uppercase is another factor. Because the letters are all converted to uppercase, the number of potential possibilities underneath the hash is reduced in half. Use of the DES. To be fair, at the time of the use of DES was still considered to be somewhat strong. Now with the current technology, even released since 1990, DES can be broken. Passing the salt. Something we will talk about in a moment, known as salt or salting, is not used in the LM process and therefore makes the protocol vulnerable to some offline attacks, such as rainbow tables. And afraid of change. LM hashes only changes used when users initiate a change on their password and not until then. This exposes vulnerabilities that could be exploited by the hacker later. So let's take a look at the hashing examples. In this case, we're looking at the output to be right over here, 128-bit, and then hex that equals 32 characters. So if all we're going to output is the word Superman, which is right here, this is the output. It is 32 bits in length, and if you want to, we take Superman and we convert it to, this is an MD5 hash value. So as you see, it's 32 bits in length. Now we're going to take this. This is out of game, this whole sentence. If you notice, this is one word, 32 characters. Here's a complete paragraph or sentence. And again, what does that convert to? A complete 128-bit, 32-character hash. So even though it's the same length, it is. Here's our shopping list. This is a text document right here. And again, what does it convert to? Well, it gives me the same 128, 32-bit characters. We have a picture down here, and that converts to this. So if we sent any of this, if I sent this picture over the internet to someone, and we want to verify that it's the exact same picture, it wasn't altered, we can look at the hash. If I know what it is, I can send the person, hey, this is the hash output, this is what you should get. Same with your shopping list. So if you're sending something over an email or a text file and you want to ensure that it wasn't altered, well, you can set up a hash and you can always verify that that hash has never changed. And that's one of the nice things about using the hash. So here's a hash function. It's the same thing. Here's our input. Doesn't matter if it's a couple letters or a complete paragraph. We go through our hash function. In this case, you can see it's exactly the same length because we're using the same hash function. So it doesn't matter what the input is, the output is always going to be the same. Whatever my hash function is, whether it's 28 or 64 or 256, whatever my length is predetermined in my algorithm in here, it gives me my output. So how can we use this to verify passwords and stuff in databases and in searches? Well, here's our data record. So this is what I am storing. I just have a 98. So what happens if I pull up, I type in my login and password, what it's going to do is it sends it to a hash, which is going to, in this case, turns out to be 98. It looks in my database, my data buckets here, and it finds 98. And then it says, hey, this is what I should be doing. This is Sam. And this is what I need to be doing right here. So by me typing in Sam, it verifies, it converts it to my hash and verifies it. So the same with Kathy. If I look here, she types in her login and password. It comes over to here, it converts it to 103, finds it in my table as 103, and then it verifies who that person is. So it keeps track of what it is. This can also help us with search engines. So I can have certain words or information that it puts in there for me, and it allows me to look at my data and search the database quickly. Instead of me searching for a common thing, common word such as jellyfish, well, it converts it to a hash. Instead of looking me through the internet, I'm looking for a hash instead of a specific number that allows me to do it a little bit quicker. So I can search for information like that. Now let's take a look at a digital signature, how this works. If you've ever signed anything online, this is what you're going to have. So here's my document, my original document. This is the one I signed right up here. So this is the one I read, and I'm looking at it and say, okay, I do agree with this. So I send it through my hash. It comes down here. I go through my algorithm, and I get my one-way hash key, my number, which would come out right here. And then I want to encrypt it. I then will send through my private key encryption and sign this. Then what will happen is we send both of these documents. This original document will come through the internet and my digital signature comes through. It gets to wherever I'm going. So my original document, which was unencrypted, there's no information in it that I didn't care if anyone saw it. It just was sent directly over the internet. It comes back over to here. I didn't change anything. I didn't look at anything. Then my algorithm right here can go through. It takes my original document and it gets hashed. And over here I have my one-way hash, right, for this document. This way, the person who sent it to me knows what I didn't change anything, because now we're going to on and hash it over here. So over here, my digital signature comes through. I have my key that comes through, my public key, and they unhash this number. Let's say if this number, let's say, was just 56 here. Obviously, that number would be much longer. When they unencrypt it, they're going to check this to be 56. Then what they're going to do is they look up here. Here's my original document that they sent me. This should have that 56 on it. So when they unhash it, when they hash it, not unhash it, when they hash that document, that number should be 56. Now, what happens if that number comes out to be 63 or 57? Well, that means if that number changes at all, that means I made a modification to that file. And that means that I changed something in here, and then they can verify, hey, you changed something, the hash didn't work right, what modifications did you make? And it can send up a red flag. So it's important that, the hashing works with the digital signatures, and it allows us to verify data that we can. Now, if we wanted to, in a separate process, I could, if I didn't want anyone to see what this is, I can send this through a encryption process, cipher it, send it through as ciphertext, send it over the internet. They can uncipher it, so we can have my digital key ciphered, my original document ciphered if they wanted to. So there are other options that we can do with this, but this is just a simple case just for a digital signature, and it just verifies nothing got changed. And that's what makes it so wonderful and important, that nothing changes. So what did we do for chapter 5? Well, we talked about the fundamentals of hashing, and we really got into depth. I know we mentioned hashing on the first week, but now we got a little bit more in depth to it. So it's a one-way encryption process. It pretty much guarantees me that the file is unchanged. Produces a digital message. Produces a message digest. So if I determine it's a 128-bit message coming out, it's going to be 32 characters. It will always be 32 characters. Doesn't matter how long my document is. It could be a 100-page document. It takes it and puts it into 120-bit. It could be one word, as we saw in examples. It does not matter what the input is. It will always have the same fixed length outcome. And that's an important thing to keep in mind. So what are some of the purposes we can use of it? It verifies the integrity of the message, especially for downloading. So anytime you download a file or you're downloading a program from like Microsoft or wherever you do, they want to make sure that you got the complete document, that the whole file is there. So in the background, they run this, and it verifies that whatever the output is, whether it's a 128 or 256 or 64, it doesn't matter. They verify that the integrity of the message that you got was still there. It doesn't preserve the confidentiality of the message, which is an important distinction. All it does is verify that the message is intact. Like I said, in the example I sent you of the digital signature, all it did was make sure that I didn't mess up the original message. If I wanted that to be encrypted, the message, I could have had that encrypted over the internet, but that is a separate process. Digital signatures, verifies files. These are just some of the applications of it. Obviously, I have that spelled wrong. So that is chapter 5 on hashing. We'll talk. Smile. Have a wonderful day.